Now it is. Now we're working. Okay. So, first of all, I'm going to just explain a little bit about our understanding of epilepsy as it is at the moment. And what an epileptic seizure is a behavioural change due to an abnormal discharge of neurons of the central nervous system, of the cerebral cortex, the bit that's like a walnut over the top. And epilepsy is a tendency to recurrent seizures. But seizures don't occur in isolation. They're a symptom of something going on. It's like lightning doesn't happen on a sunshiny day. There has to be the right condition, and the right condition is usually some form of structural change in the brain. And what that structural change is depends on who you are and critically how old you are. So there are some conditions that will trigger epilepsy in young people, particularly developmental disorder, birth injury, and so forth. But the commonest age for epilepsy to start is actually in older people, and I feel this in myself, racing towards the time of cerebrovascular disease, dementia, and tumours, which are the commonest underlying causes in that age group. That gives us a very complicated looking classification, where we have different kinds of seizures combined with different causes in a sort of Venn diagram, leading to what we call epilepsy syndromes. But fortunately, there are only two words that I need you to remember on this slide, and they are focal and generalized. So this is an example of focal epilepsy. You'll see on the top there's someone with a tumour on the brain scan, and you'll see on the bottom panel the electrical pattern from electrodes over the whole scalp, showing the spiky discharges on some of those electrodes, representing a focal epilepsy. That electrical discharge is only over part of the brain. Now, that electrical discharge may remain in that part of the brain, or it may spread over the whole brain. If it remains in that part of the brain, then the symptoms of that seizure will be a corruption of the normal function of that bit of the brain. So, for example, if you have a seizure starting in the visual part of the brain, you may have visual hallucinations. Or if you have a seizure that starts in a bit of the brain controlling your right arm may twitch and jerk. Then, if the seizure spreads over the whole of the brain, you might have what people most commonly recognize as a seizure, which is a collapse with convulsion, which is technically called a tonic-clonic seizure. So since the brain does lots of things, there can be lots of different symptoms of epileptic seizures. The other kind of epilepsy is generalized epilepsy. There's a structure in the middle of the brain called the thalamus, and that structure is involved in regulating the activity of the cerebral cortex. So, for example, it has a switch built in that changes the activity between waking and sleep. And we believe that generalized epilepsy is a disturbance of the interaction between the cerebral cortex and this deep structure. So the electrical abnormality, which you can see in the panel on the lower right, seems to start over the whole brain at the same time. Now, the manifestations of seizures in generalized epilepsy are much more limited. Tonic-clonic convulsive seizures, absences, and sometimes some other types. So, now let's see if this works. No, it's not going to work. So, this is my pièce de résistance, which is a lion having a seizure. And I can't show it to you, unfortunately, but I will act it out for you instead. So, what happens here is that the lion starts to have some true movement. Like this. Those sorts of movements are often seen in seizures that arise from the temporal lobes when the discharge spreads to a deeper part of the brain. You can perhaps see that lion's eyes are turned to the left. Can you see that from where you are? So, as the seizure progresses, the lion's head is going to turn to the left, and he'll continue chewing, and then he'll keel over and start to convulse. So that turning of the head and the eyes tells us that the seizure is starting in the right hemisphere, on the opposite side to the head turning. So I'm sorry we can't show you that, though that's obviously something to show you afterwards. So that's what we think about epilepsy at the moment. Is that all clear? Fully understandable? Excellent. So we'll move on to what people thought about in the past. And this story starts in the Akkadian Empire, which is in Mesopotamia, where somewhat later Alexander the Great had his empire. And I know that as I go through these slides on history, I will be touching on subjects where people in the audience perhaps know much more than I do, and so that's a little awkward, but bear with me. They called epilepsy antasu, the hand of sin. And we have in their writings clear descriptions that we can recognize as tonic-clonic-convulsive seizures. And they believed that seizures were brought on by the moon, by the god of the moon, and they were treated by exorcism. Now this kingdom only lasted 180 years, and to the north it became Assyria, and to the south it became Babylonia. And we have the general medical textbook of the Babylonians, written on stone, called Sakiku, by a chap called Esagil Apli. And they kept the name Antasubu for convulsive seizures, but they also recognized focal seizures causing convulsion of one side of the body, which they called nicotine. And again, they recognized that a person could be conscious during those seizures, but it was, again, demonic possession that was the cause. Hippocrates was having none of it. So he wrote on the sacred disease, "The alleged divine character is only a shelter for ignorance and fraudulent practice." So he had a very organic view of epilepsy. He believed that the brain was the cause, and he believed that it should be treated with diet and drugs. Not very different from how we would think about it. For humans, black bile, yellow bile, blood and phlegm were gaining credence as the basis of all disease, something that continued really for the next 2,000 years. If we go to Italy and to Alexandria, there were a number of people who undertook what we would consider to be experimental method in investigating. We wouldn't necessarily think it was entirely ethical what they did. They undertook dissection of animals and dissection of humans. Okay. Vivisection of animals, getting a bit doubtful. Probably also vivisection of humans, a bit uncomfortable with that one. And they identified that consciousness came from the brain, whereas beforehand people hadn't quite known whether it came from the brain or the heart. And they identified motor nerves that move from the nervous system to the periphery, and sensory nerves moving in the other direction. And then we come on to Galen, who developed the ideas for humans, and he thought that epilepsy came from the brain, or perhaps it came peripherally with all that convulsion going on and went into the brain. There are some seizure types where patients will feel a rising sensation in their abdomen, and we call that an aura, or wind. That's a meteorological wind rather than a gastroenterological wind, and he believed that epilepsy could sometimes start in the stomach as well. And he wrote a detailed treatise about how to treat a young boy aged 10 with epilepsy, recommending diet, fruit and nuts, exercise, and drugs, something called squills, which is lily flower with vinegar and honey, which doesn't sound too bad. Around the same time, we had St. Valentine. St. Valentine is better known for his romantic connections. At the time, it was illegal for Roman soldiers to marry because the thought of their beloved wife at home might put them off the serious business of war. And he undertook some illegal weddings, following which the soldiers could avoid conscription. For his efforts, he was beheaded, or executed anyway. Guess what date? What day of the month? That would be the 14th? Yeah. So the that's his link to Valentine's Day. His link to epilepsy is rather more uncertain. And some people simply think it's his name, Valen, which is similar to the German Fallen, meaning to fall. But whatever the link, he is the most popular patron saint of epilepsy, and he appears in numerous works of art through the medieval period. But there are other patron saints as well. Hildegard of Bingen was a woman whom you may have heard of through her music, which is still performed today. She was a truly remarkable individual. She is one of the founders of the science of botany. She was a theologian and a physician. She herself suffered with visions, and like almost every other person who suffered with visions in the past, some doctors said she might have epilepsy. But she did talk about epilepsy, and she talked about it in terms of a humus and a very physical basis, of the mechanism. But in terms of the underlying cause, she wrote, "May you preserve yourself from that which is not of God, and which is done with the left, the sinister hand, lest you fall in the falling sickness of pride like the first angel Satan." So she believed a physical mechanism, but a spiritual cause. And she identified different personalities that could contribute to the development of epilepsy: the angry type and the amoral type. But that's not the only idea that was circulating around this time. And this man, Bertolt of Regensburg, believed that contagion was the cause. Of course, this was a time when no one had heard of microorganisms. So he's quite prescient. And we might think about that in the time of COVID, when he says, "Don't go near him, for such a terrible breath comes forth from his mouth, that you may acquire the same disease." Paracelsus was one of the founders of modern chemistry, and he believed that the internal milieu was balanced by the external milieu in the universe, and that things going on in the universe could change and cause illness. And in particular, epilepsy, he believed that conjunctions of the Moon, Saturn, and Venus were the underlying cause. But gradually, we're coming back to things that might be more familiar to us. And this Portuguese called Velasquez de Taranta recognized different kinds of seizures. So he again recognized focal seizures, which had largely been forgotten about. But he also recognized that certain kinds of brain injury cause seizures, such as head injury, or the association of epilepsy with syphilis affecting the nervous system, and also a fungus which infects rye, called ergotism, producing a drug called dicotomine, which until quite recently was used in the treatment of migraine, but in toxic doses can cause seizures and a range of other problems. In this country, we really think the father of neurology is this man, Thomas Willis, not least of which because he coined the term neurology. So without him, I wouldn't have been a neurologist. And he attributed seizures to disorders of the brain and the nerves, and he had a scientific method in which he conducted post-mortems to establish his views. He also noted that epilepsy sometimes goes away around puberty, and wondered if there was some kind of sexual component. So that's what was going on in this part of the world. But I'm just going to take you on a very rapid journey around other parts of the world to see what they think about it. So in China, in the Zhou dynasty, they adopted the term Dian. I don't know if I'm pronouncing that correctly, for epilepsy. And they recognized several different types. And they classified it according to the noise that the patient makes during their seizure and what animal it sounds like. And they believed that epilepsy came on, was due to disease of the visceral organs in the time. And their treatments were herbs, acupuncture, and massage. But there were other beliefs in China as well, and this group, the Hmong community in China, again had a spiritual view. They regarded all diseases as spiritual displeasure, but because in epilepsy the spirit entered the body to cause the epileptic manifestations, this was actually a blessing. Going to India, they have various types of medicine there, but Ayurvedic medicine has a very long history and is still practiced. And they had something called the doshas, which were quite similar to the humours that we had further west. And they had some ideas which they expressed differently, but I think we would recognise as a departure of memory, which I think we can interpret as alteration of consciousness and amnesia, and they recognised it was due to problems in the brain. They described convulsive seizures, and they also recognised certain structural causes, such as congenital malformations, stroke, and they treated it with drugs and diet. Going on the other side of the world, the Aztecs, much more recently, had a goddess of epilepsy. She was also the goddess of filth, called Tlazolteotl. And they believed the sufferers were blessed. They too recognised that focal seizures, auras, and convulsive seizures were part of the same disorder. And going further south to the Incas, around the same time, they believed epilepsy was due to avenging ancestors. And in fact, you can see in the picture there the wife of the last ruler before the Spaniards took over, a lady called Chimbo Nanakaba, suffered with epilepsy. They discovered 800 Japan skulls amongst the Incas, and we don't quite know why they did it, or even if it was a treatment for epilepsy, but what we do know is that they were pretty good at it, because quite a lot of the skulls are well healed, which means that the people survived the experience. With trepanation in this part of the world, rarely led to survival. And people speculate that the reason for that may be that the air was nice and cleaner in the Andes, whereas in a European city at the time it was perhaps rather more dirty, so infection was much more likely. I mentioned a bit earlier about historical figures and being claimed to have suffered with epilepsy. And I've put up 3 here as a sort of spectrum of likelihood. So starting with Muhammad, it has been written that he may have suffered epilepsy on the basis of a single sentence where he said, "I see a vision of the angel Gabriel and not being able to bear the sight of him, I fall down." That seems to be a highly dubious suggestion of epilepsy. Joan of Arc, you'll notice she was only 19 when she died. She described, "I hear this voice to my right, rarely do I hear it without also being accompanied by light, and the light comes from the same side as the voice." So something that is anatomically as localized and specific as that is much more likely to be epilepsy. So I think there's a definite possibility there, although of course it's true. Dostoevsky certainly did have epilepsy, at least he told us he did, and he had a form of epilepsy which is called ecstatic seizures. You remember I said that an epileptic seizure can be a corruption of anything that the brain can do normally. So he described, "You are all healthy people, but you have no idea what joy that joy is which we epileptics experience the second before a seizure. I do not know whether this joy lasts for seconds or hours or months, but believe me, I would not exchange it for all the delights of the world." And he put this into one of his characters, Prince Mishkin, in The Idiot. So now I want to move to more recent times and really the development of our modern understanding of epilepsy. And in this country, these 2 men are key. The guy with the beard, you might guess that he's in the 19th century. The guy with the beard is a man called Hewlett Jackson. And he undertook postmortems in a range of different neurological conditions and was able to relate the location of the abnormality with the nature of the symptoms that the patient has suffered. So he got this much more precise anatomical relationship of symptoms to disease. And he was sufficiently accurate that when when someone came to him after an accident with seizures causing unilateral convulsions, he was able to turn to the other man in the picture, Victor Horsley, and say, I think if you operate on that bit of the brain, it may make the epilepsy better. And Victor Horsley undertook the first successful epilepsy surgery in 1876. This man showed us that epilepsy is due to an electrical disturbance in the brain, and he was the first person to record the electrical activity of the brain with wires over the top of the head. And from that point, we then have a marker of the disease. We don't have to look into the brain anymore. A man with a complex legacy in that he also wrote, I'm gladly willing to work again as an assessor of autogenetic health for the Nazis. So, Walter Penfield was a remarkable man. He was the first neurosurgeon in Canada, starting work in about 1930. And he really is the person who advanced epilepsy surgery. What they would do, they would anaesthetize the patient with epilepsy, they would open up the skull, they would put electrodes directly onto the surface of the brain to try and identify where the abnormal electrical discharges were coming from. They would then wake the patient up and stimulate the brain to see if that part of the brain did anything too important and an operation would harm them too much. And then they would do an operation to remove the abnormal brain. And he was the one who gave us the homunculus, which you can see there, the little man, showing that the bits of the brain devoted to looking after your mouth, face, and hand are much bigger than the ones looking after your foot, reflecting the relative importance of those structures. Sometimes when I see patients in the clinic, they say to me, I don't understand why I've got epilepsy, there's no one else in the family. So I thought it would be interesting for you to ask yourselves the question as we talk about epilepsy, what the likelihood is in the average person if a parent has epilepsy, that their offspring will have epilepsy. I'm not going to ask for a show of hands, but the answer is generally less than 5%, although there are specific forms of epilepsy where there is a major component. And of course, the genetics starts with this man, Gregor Mendel, who identified dominant and recessive inheritance looking at P's, but it was largely forgotten about until it was adopted at the beginning of the 20th century in the eugenics movement. And in the United States, the case Buck versus Bell upheld compulsory sterilization for people with epilepsy in 29 states. And in the 1950s, it became 17 states, it became a crime for anyone with epilepsy to marry or to knowingly marry someone with epilepsy. And this was repealed within memory. Just in case you think that's over the pond, in the land of things weird. In the UK, the Matrimonial Causes Act in 1937 made it legal to annul a marriage within the first year if either partner had epilepsy. And again, only repealed in 1971. So I've covered a little bit about history, a little bit about culture, and now I'm going to talk a little bit about treatment. So these are the abbreviations for the list of drugs that we have. The first drug of the modern era was phenobarbital, which was licensed in 1912 and is still very widely used, a very effective drug. You can see in the last 30 years there's been an explosion of new drugs. And this is where we come to the science. So, nerve cells, and there are about 80 billion of them in the average brain, talk to each other with connections called synapses, of which there are trillions. A nerve cell has an electrical impulse that travels down the nerve cell and triggers the release of a substance. You can see the substance in the little bubbles, called a neurotransmitter, which crosses that tiny gap to the receptor on the other side to trigger the electrical impulse in the next cell of the chain. Those electrical impulses are generated by charged ions, mostly of sodium, potassium, and calcium. So we've got neurotransmitters and ions that move through channels, which are little pores in the cell. There'll be a test on this slide afterwards. Essentially, all the drugs that we have in the treatment of epilepsy work on these mechanisms. How well do they work? So, if a patient comes to the clinic, the first drug I give them, I would expect that about half the patients will be rendered seizure-free. And about another quarter, if we manipulate the drugs, change things around, eventually we'll hopefully get them seizure-free. In another quarter, we will never get them seizure-free, whatever drugs we use. They might go into a spontaneous remission, that does happen, but our drugs won't do the job. So we have to think about other things, and here sometimes we might think about surgery for the epilepsy, but very often it's a question of helping a patient manage the problem rather than eliminate it. So can we do better? This is where we come back to genetics. And just to remind people, your genes are in your DNA. Your DNA is translated into proteins. Proteins do all the jobs of the body. All the chemical reactions, all the structures are created and managed by proteins. On the way to a protein is something that's an intermediate called messenger RNA and mRNA. There are also large parts of your genetic material that do not go into making proteins. These are non-coding bits that may have some influential function on genetic expression. So we've got gene, protein, and function. And we can try and influence those with small molecules, either at the protein level or at the gene level. Or we can try changing the genes themselves. And to think why this is important, I'd like to look at this slide. So if someone has a major head injury or a stroke, they might develop epilepsy. But they might not develop that epilepsy for months or years later. So what is happening during that time? And can we intervene in what is going on? Because all the treatments that I've shown you just treat the electrical activity itself. They don't treat the underlying causes. And if we had something like that, could it change the epilepsy even once it's been established? So in the top panel there you can see a healthy genome ticking along, producing proteins of various different types at a steady level, green arrows horizontal. But after an injury, the genes change massively. Some have much greater levels of expression, some have much reduced levels of expression, and that may then result in a disease. And we're starting to understand what those genes do, but it is hundreds and thousands of genes that may change, and we have to work out which ones we want. There's inflammation after an injury, which is not surprising. There's cell death. There's cell division. There may be genes that influence reorganization of nerve cells, the rewiring, and there may be genes that influence changes in the receptors and the channels that are important and that our current drugs work on. So how can we influence that? There's a condition called tuberous sclerosis, which some of you may know about. It's not rare. It's a genetic condition, and it is due to a genetic abnormality that causes a problem with regulation of cell division. So people sometimes suffer different kinds of tumours. For example, these little tumours on the face. They're tiny little things, they're not malignant, but they're just a marker of the disease. It can also cause tumours in the brain, and you can see one highlighted in the red circle there. Now, we have a drug called everolimus that interferes with the gene product and can affect cell replication as a result. And that drug will cause tumours caused by this condition to shrink. The pathway that interferes with is called mTOR, and the drug basically blocks mTOR. And you can see that after treatment, 3 months treatment in this child with this tumour, it has shrunk. Now, these people with tuberous sclerosis often suffer with epilepsy even if they don't have tumours. And so the question is, if we interfere with this gene, with this drug, can we help the epilepsy? And the answer is, even if the epilepsy is already established, there are certainly cases that get better with this drug. And the question then, of course, is what would happen if you gave it before the epilepsy ever started? So that's a small molecule, and I think gene therapy is starting to become a bit more familiar to people now that they've heard about ways of developing COVID vaccines. But this is basically how it works. You take a virus, you take away the bits of the virus that make you ill, you add a bit that helps the virus target a specific tissue so it ends up in the right place. And that's tricky with the brain because the brain is hard to get to. And you then add a bit that changes the gene that you want changed in your target tissue. So the virus arrives in the tissue, inserts itself, replicates the gene that you want, and alters the function of the tissue. There is a wrinkle that you can add to that. You can make it so that the gene only starts working when you give another drug. So it's in place, and you give this other drug like a switch. You switch on the gene, perhaps the gene for epilepsy, for control, the patient gets better, and then perhaps after a few years you think, well, I wonder if we need this anymore. And then you start the small molecule, the gene switches off and just sits there and does nothing. This is an approach that is currently close to trials in humans with epilepsy. So I'm hopeful that as we move from drugs that treat seizures to drugs that treat the underlying mechanisms for the development of epilepsy, that we will see a reduction in that 25% of patients whom we currently fail to treat. So I hope I've given you a picture, an understanding what epilepsy is, how we think about it now, how it has changed over hundreds of years, that this is, like very few other illnesses, embedded in our culture. That we have treatments that are reasonably effective, but we are on the verge of treatments that really offer new horizons for treatment of this condition. And I'll leave you with Raphael's Transfiguration, with Christ coming down, and you can see a quote from Mark, and you can see the boy at the bottom right of the picture with seizures that he is being asked to treat. So thank you very much, and I think we finished on time. We won't take any questions.